Another type of question that frequently involves complex numbers is about the roots of polynomials. So I want to talk a little bit about that today. We're going to be talking about polynomials of degree bigger than 2 to be interesting. Here's an example with degree 3. And I've written it in general form with coefficients a, b, c, d, but that's not the most interesting way to write it. Now I'm writing it in factored form. I have kept the letter a because I had already used it here. And when you do the distributive in all of these factors, you will get a times x times x times x, which is ax cubed, the same as up there. And then you will get other terms in x squared or in x or a term without any x. Now for these here, I have chosen different letters than in the previous line. P, Q, R, because they do mean different things, right? P, Q, and R here are the roots of this polynomial. They are the zeros of the function, just because of the null factor law, right? When you want f of x to be equal to 0, then because this is a product of many things, in order for the product to be equal to 0, then you know that either this is equal to 0, or this is 0, or this is 0, which means that x needs to be equal to either p, q, or r in order for the function to be equal to 0. So doing the whole distributive here would be way too much, but there are some interesting conclusions that we can take from just doing parts of it. For example, I've already said that when you take the x on all three factors, then you get ax cubed, just the same as you had in the first line. But how would you get the b? How would you get the x squared? Well, you can either take these two x's and that r, or you can take the first x, the q, and the last x, or you can also take the p with the two other x's. Of course, they are all carrying this minus sign that they had in the factored form, and also the a is going to have to be multiplied in front of everybody. But when you do that, you get what? The term in x squared, so that is bx squared. And when you divide both sides of this equation by x squared, you just get this. And then you can divide both sides by negative a and find that the sum of all the roots of the polynomial is equal to minus b over a. I'm doing this example with degree 3, but it would work exactly the same for higher degrees as well. And you could keep doing that for all of the coefficients like c, but it turns out that the interesting thing, at least if you're interested in exam questions, is not going to be all the coefficients, but the last one. So we are interested in this one that gave us the sum of the roots, which is always going to be minus this coefficient over this coefficient. But then we don't care about the intermediate coefficients, and we are again interested in the last one. Because how do we get to the last coefficient in the distributive? You have to get the a and then none of the x's. You're just going to get the p, the q, the r, because that is the coefficient of the term that is constant, right? There is no x here. So that is the d term, which in this case, because the degree was 3, which is an odd number, I'm getting minus, 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 so it's giving me minus a and then pqr, which is the product of the roots. Just keep this little detail in mind, because if you get something of even degree, then you won't get this minus in this formula. But the minus on the formula for the sum of the roots, on the other hand, will always be there. These formulas are in the booklet, but of course he doesn't want to do it in an example of degree 3 like I was just doing, so he has a generic degree n here, which is why he needs to write his polynomial in sigma notation. And here is the fact that we were just talking about. The negative sign in the sum is always there, but in the product, there is a minus 1 to the power of n, which makes it alternate between odd and even degrees. So if the n, which is the degree, is even, then there will not be a negative sign, which is exactly what we were just saying in the example. Okay, so as for polynomials, I think that's the only thing that I need to tell you before we start looking at exercises. But I also need to tell you one thing about complex numbers, which is the fact that when you have a polynomial like this, and I'm talking about polynomials in which the coefficients are real numbers, of course you can have some roots that are complex numbers, right? We've already known that ever since just quadratic functions, which are polynomials of degree 2. Sometimes they don't have any real roots, like in this example. And this happens exactly when, in the quadratic formula, we try to take the square root of a negative number. So when we're looking for real roots, that's not allowed. But when we're looking for complex roots, Of course it is allowed. That's just the imaginary part of the number. And here's the interesting thing that I wanted to point out. Even in the quadratic formula, you have this plus or minus in front of the imaginary part, because I'm talking about the case where the roots are not real, right? So that square root in the quadratic formula in this case is the imaginary part of the complex numbers. And you have a plus or minus in front of that. You're always going to get a pair of roots this way, one with a plus and one with a minus in the imaginary part. So what that means for the complex numbers is that one of those is the conjugate of the other. And it turns out that this is always the case no matter what degree the polynomial has. The complex roots are always going to appear in conjugate pairs. So if you have a number z that is the root of a given polynomial, then z star is also another root of that same polynomial. And this fact is explored a lot in exam questions. Just keep in mind that I'm only talking about polynomials where the coefficients are real numbers, okay? If the coefficients themselves are complex numbers, then this is not going to be the case anymore, but I don't remember having seen an exam question where that happened. So anyway, here's a very good example of how this type of thing appears in exam questions. You have a polynomial of degree 4. This p is in R here is one of the coefficients, and the other ones I can already see that they are also real numbers. And he gives us 3 of the roots. He gives us this complex number and then an alpha and alpha square that are going to be real roots. But he gave us only 3 of the roots when we expect there to be 4, because this is the degree of the polynomial, because he is trying to test if we know that 3 plus I being one of the roots implies that 3 minus I is another one of the roots. So he didn't give us the 4th one because he expects us to know. And then here's the other 2 roots. I am going to multiply all of them together instead of adding them because I don't know this coefficient p here, so I'm not interested in looking at the sum. But I do know that this is 80, so this is what I'm going to use, because the product of the roots is supposed to be 80 over 1, because this is the leading coefficient here is just 1. And in this case, there is no negative sign to put on the 80 because 4 is an even number. So I'm just going to multiply here. 9 plus 1 is this times this, because I'm using a special product, and the fact that I squared is equal to negative 1. And then multiplying by alpha to the power of 3 is equal to 80. Obviously, this is 10, so alpha to the power of 3 is equal to 8. And then alpha equals 2, which is what I wanted to find in the part A of this question. So naturally, part B is asking me for the value of p, right? It was the unknown coefficient over there. And I am going to use the sum of the roots to get to that. The sum of the roots needs to be negative p, and I already know all the roots. It is 3 plus I, 3 minus I, 2, and 4, because it was alpha and alpha squared. So I cancels out with negative I. Now I have 3, 6, 8, 12, and then p is negative 12. That's the end of this question. Second question is very similar. I also have an unknown constant m being used in the coefficients of the polynomial. It's being used in a more complicated way, right? Because it appears 3 times. And my polynomial has degree 3. He's giving me information in a slightly different way that he was giving me before. Instead of telling me the roots, he said that z minus 3i is a factor of the polynomial. But that is just about writing polynomials in factored form, right? If z minus 3i is a factor, that just means that 3i is one of the roots. So if I have 3i as one of the roots, I also need to have negative 3i as one of the roots, and then I need one more. I'm going to call that one x because I know it's a real number, so I don't want to call it z. And the reason why I know that it's a real number is because I only have one more root to find, and so it can't be complex because the complex roots always appear in conjugate pairs. I can't find 2 more here, just 1, so it has to be real. So I'm using the formula for the sum of the roots here. The coefficient in the z squared was 36 over m, and the coefficient of the z to the power of 3 was negative 1, okay? So that's just going to be 36 over m. And now I am going to do the same thing for the product of the roots. In this case, I do have a minus sign because 3 is an odd number. Now I'm going to put 4m divided by minus 1, which obviously is just 4m. Now 3i minus 3i cancels out, so I have x equals 36 over m. And in the second equation, I have minus 9 times I, so that's plus 9 times x is equal to 4m. That is my second equation. I have two equations in two unknowns, x and m. What I want is to find x, right? Because he asked me to find the roots. I already have two roots. I need one more, which is x. Okay, so I'm just going to substitute m equals 9x over 4 into this equation over here, which is going to give me x is equal to 36 over 9x over 4. This cancels with that. It's 4, so x goes over there. X squared is equal to 16. X is equal to, well, plus or minus 4. But now I'm going to have to decide between those two because it told me that m is positive. And this is telling me that x and m have the same sign, so x is positive as well. There you go. X is equal to 4. The third question is again giving me a polynomial of degree 3. He gives me a couple of the coefficients. D and E he doesn't give me. He just says that they are real numbers. Alpha, beta, and gamma are the names that he uses for the three roots. And for right now, he just wants me to show that I know how to handle the sum of the roots of the polynomial, which needs to be 7 over 2, because there was a minus there, but there's also a minus in the formula. So I'm putting that information here because I think I'm going to need it for part B, in which there is a completely different polynomial now, polynomial of degree 5, for which I also don't know all of the coefficients, but I know that they are real numbers. And I know that these same numbers, alpha, beta, and gamma, are also roots of this new polynomial. He is giving me another root here by saying that this number satisfies this equation. So first of all, I know that p minus 3i is also a root because it is the conjugate of the root that he gave me. So now I don't know all of the 5 roots, but I do know the sum of all of the 5 roots, because the first 3 added together is 7 over 2. And then I have the p plus 3i and the p minus 3i. These things cancel out. And I also know the total sum of the roots, because of these coefficients here, is 11 over 2. And now I just found out that p equals to 1, exactly like he wanted me to show. Now, I wish he had said somewhere in the question that p needed to be a real number so that this complex conjugate that I'm using here is 100% correct. But then again, since it was a show that question, I know that I've actually done what he wanted me to do, because p is equal to 1. And now this is what I know about the roots. I still don't know the difference between alpha, beta, and gamma, but I do know 1 plus 3i and 1 minus 3i because I've substituted p equals 1. Now he's telling me some things. When he says that h of a half is equal to 0, he's telling me that one of the roots is a half. And the way that I'm going to know which one it is because he's telling me that alpha and beta are integers. Well, 1 over 2 is not an integer, so it can't be that one. And gamma is a rational number, so I know that gamma is the one that is a half. And I know that the product of all the roots is supposed to be, well, let's go back to the coefficients. There is a minus 20 here in an odd degree polynomial, so that's 20 over 2, which is 10. I also know how to do this multiplication here, which is going to be 1 plus 9, which is equal to 10 as well. So this cancels out with this. And the thing that he's asking me, which is alpha times beta is equal to 2. Now he wants to know the value of alpha and beta. Well, they multiply together to 2. They are both positive and they are both integers. And alpha is the smallest one. So the only way this works is if alpha is 1 and beta is 2. So those were the questions that I wanted to show you about this topic. As you can see, they are not difficult, but you do need to know these things. the sum of the roots, the product of the roots, and the fact that complex roots always appear in conjugate pairs. You can solve a bunch of exam questions just with these things.